Okay, we are welcome to the fourth series of this preparatory class. Now, today we'll be considering number system, or what we simply call numeration. So the number one types of number, we want to consider types of number, and the number one here is natural numbers. What do we mean by natural numbers? We define it as positive counting numbers. So like 1, the least is 1. They are all positive. 1, 2, 3, 4, 5, 6, 7, 8, up to infinity. Number 2, we have whole numbers. How is whole numbers different from natural numbers? The whole numbers, here we say these are natural numbers, including 0. Why natural numbers are basically positive counting numbers? The whole numbers are positive counting numbers, including 0. 0 too is a whole number. So we have number 3, we have integers. What do we mean by integers? This one is, we say positive counting numbers, including 0. That is, we are talking about whole numbers, and negative integers. That is, when you have from -1 to -2 to -3 to -4 to -5 up to minus infinity. And you also have from 1 to 2 to 3 to 4 to 5 to 6 up to positive infinity. Then, including 0, all of them together, we call them integers. All integers too, you can see too that they are not, integers are not decimals. They are not decimal numbers. That is, they don't have a decimal number, a decimal, simply decimal, or sometimes, if you, or unless you want to call it decimal number, but basically we call it decimals. So, and when you talk about decimals, decimals contain 2 parts. We have whole number parts and we have the fraction parts. The numbers after the decimal point is what we call the fraction part, while those before, or that before the decimal, is what we call the decimal operator. That's the one we call whole numbers. Then we go to even numbers. Even numbers are numbers that are divisible by 2. 2 can divide them directly without any remainder. So like 2, like 4, like 6, and so on. But it's important for us to know that even numbers, as we advance, especially maybe secondary school, even numbers is not limited to positive alone. Even number can be positive and could also be negative. We can have negative even numbers. The same thing holds for odd numbers. Odd numbers are numbers that are not divisible by 2. They are the opposite of even numbers. They include 1, 3, 5, 7, 9, 11, 13, 15, and so on. So as we have positive odd numbers, we can equally have negative odd numbers. But most of the time when we talk about even numbers, we just consider the positive, unless there's need for us, or unless it is indicated that we should also include the negative in our listing. So the same for odd numbers. Then here we talk about prime numbers. Prime numbers can never be negative. They are positive. They are positive numbers. So, and here we say they are positive integer. A prime number is a positive integer greater than 1. The list of a prime number is 2. A prime number is a positive integer greater than 1, and which is divisible by 1 and itself. That is, it only has 2 divisors, 2 factors, which are 1 and itself. That is, it has only 2 distinct factors. The word distinct here means that, for example, some students may make mistake and say, is 1 a prime number? 1 is not a prime number. If you look at 1 in the first place, we say a prime number must be a positive number. But if you claim 1 is a positive number, and we define that it must have 2 factors, 1 and itself. If you say factors of 1, if you say 1 and itself, that 1 itself too is still 1. That means 1, 1. The 2 of them are not different. They are not distinct. So 1 is not part of prime numbers. The list of prime numbers is 2, we have 3, we have 5, we have 7. 9 is not there. Unlike how we have 9 under odd number, but 9 is not part of prime number. Why? Because 9 is divisible by other factors apart from 1 and itself. It's also divisible by 3, so it's not part. 11, 13, 17, 19, 23, 29, and so on. We go to perfect squares. Numbers whose square roots are whole numbers, they are perfect squares, or numbers that is expressible, a number that is expressible in the form x squared, where x is a positive counting number. For example, this one is 1 square, this one is 2 square, this 9 is 3 square. 4 square is 16. 62 is part of prime, perfect square. 25, 36, 49. But if you take square root of each of them, it will give you a whole number too. So for example, square root of 1 is 1, square root of 4 is 2, square root of 9, that is the number that multiplies itself to give 9, is 3. Square root of 25, the number that multiplies itself to give 25 is 5. Square root of 25 is 5. Here we have composite numbers. Composite numbers. These are positive numbers which have more than 2 proper factors. Let me quickly define this. The difference between factor and proper factors. If I talk about, okay, permit me to type here. If I just say factors of 6, for example, include 1 can go in 6 directly, 2 can divide 6 directly, 3 can divide 6 directly, and 6 can divide itself. These are factors of 6. But if I talk about proper factors of 6, proper factors of 6, this include all those factors of 6 apart from itself, which are less than that 6 itself. They are proper factors of 6. All numbers that can divide 6 directly, apart from that are not up to that 6 itself. So e.g. 1 is a factor and it's less than 6. 2 is a factor, is less than 6. 3 is a factor, is less than 6. So these are proper factors of 6. So composite numbers are positive numbers which have more than 2 proper factors. For example, now look at 6. The proper factors of 6 are 1, 2, and 3. That is 3 numbers. At least 3 numbers as proper factor. Then such a number is said to be a composite number. Then there's difference between perfect square and perfect number. Here I say perfect number. This is a positive number whose sum of proper factors except itself equals to the number. Whose sum of proper factors, in fact, even this one I can see it as a kind of redundancy. Since I say sum of its proper factors, you know that once we talk about proper factors, that means the number itself is not there. But let's still accommodate it, except itself equals to the number. For example, what are proper factors of 6? 6. The proper factors of 6, 1, 2, 3. But if you sum these proper factors together, it will still give you that 6 back. 1 plus 2 plus 3 will give you 6 back. Let's take another example quickly. Suppose I want to take that of 28. The proper factors of 28, 1 can go in 28, 2 can go in 28, 4 can go in 28. Yes, 4 in 28, 7 times. 7 can go in 28, that's 4 times. Then 14 can go in 28, 2 times. So after 14, the next one is 28. But since we talk about proper factors, 28 will not be there. So if you sum all these proper factors together, you say 1 plus 2, 3, plus 4, 7, 7 plus 7, 14, 14 plus this 14, you will get 28. Therefore, 28 is a perfect number. It's different from perfect square, like we saw previously here. Palindrome, numbers whose digits read the same both ways. That is, whether you read it forward or you read it backward. For example, a 2-digit palindrome is 33, 44, 55. If you say this one is 3, 3 to the right, and backwards 2 is still 3, 3. This one 252, 252. And if you want to read it backwards, it's still 252. Look at this one now. This is 13531. If you read it, if you are reading it backwards, to be 13531. So that is what we call palindrome or palindromic number. Rational numbers. This one are basically integers, including fractions, decimal. It is important for us to know that a fraction is also a decimal, because, for example, if you have 1/2, the same thing as 0.5. And a fraction is also a percentage, because 1/2 as a percentage is 50%. So all of them, they are under rational numbers, including fractions. But not all decimals that are what? That are rational numbers. It's important for us to say that. Like we will see under number 12 here, that we say irrational numbers, numbers that are not rational. Every decimal that you cannot convert into a fraction, they are not rational. Every decimal that is convertible into fraction, they are rational number. For example, this 1/3 here, 1/3, if you convert it to decimal, it is the same thing as 0.3333 and so on. You will see that that 3 recurs, it reoccurs, it continues that way. So because this reoccurrence is predictable, it makes it very easy for us, or possible, to convert it into fraction. There's a way we convert recurring decimal back into a single fraction. But if any decimal does not take any predictable pattern, then it may be difficult or impossible to convert. So like the case of those one, we call it irrational, we call them irrational numbers. Like here, we have decimal numbers that are not convertible into fraction, e.g. pi. Some, I know you may feel pi is 22/7. 22/7 is not actually the original value, the actual value for pi. 22/7 is not the actual value, but it's the closest fraction that can take the place or the value of pi. Pi is a decimal, non-terminating a decimal. And this decimal does not take a predictable, order in its recurrence. Therefore, we see it as a rational fraction. As a whole, it cannot be converted into a fraction. So we just make use of 22/7 as the nearest fraction that is, a fraction that is nearest to the value of the decimal that pi assumes. The same thing when you talk about square root of some numbers, especially square root of prime numbers, they will give decimal that, they are non-terminating decimal and they don't follow recurring order. So they are all irrational numbers. Number 13, we have real numbers, or you say real numbers. This includes both rational and irrational numbers. You already know what we call rational now, or rational number. Basically, real number is very large. At primary school level and at secondary school level, we make use of real numbers. So you only talk about imaginary numbers in few exams, like SAT or ACT. But most of the exams that we take at primary school level, common entrance, secondary school level, WASC, NECO, UTME, post-UTME, IGCSE, all those ones, most of them they make use of real numbers. So imaginary numbers is what we want to talk about next. Imaginary numbers. What number do we call imaginary? For instance, the square root of negative numbers. You won't be able to find a defined value for it. For example, -9, square root of -9. What number will multiply itself to give -9? You can't think of it. If you think of -3 times -3 won't give you -9, to give you +9. Therefore, -9 here is square root of -9 is imaginary, unless we imagine it. It's not something that we can say this is the exact value that I want to give to it. And if we are trying to simplify it, we can now say square root of -9. -9 is same thing as 9 times -1. And square root of 9 times -1 is same thing. You can distribute the square root. Square root 2 is power. So you can distribute it here and say square root of 9 times square root of -1. And square root of 9 will give you 3. But since we don't know what to use to represent square root of -1 as value, then we call it letter I. That I there stands for imaginary. So that means square root of -9, we see it as 3i. And lastly, that's the largest of all numbers in mathematics, complex numbers. So these are comprised of real numbers and imaginary numbers. For example, if you look at this 4 now, this is the real part. And if you look at these 2i, once you say I with it, you know that's imaginary. So the two of them combined together, we see it as complex number. So if you read over and over, you'll be able to get used to all these numbers and know their differences. All right, thank you.